In 1967, John Lennon wrote a lyric casually wondering how many holes it would take to fill the Royal Albert Hall. It was written as surreal, psychedelic poetry. But by asking this question, Lennon accidentally created a specific problem of volume and density that requires a set of precise measurements to solve. Physicists have a framework for solving this exact kind of puzzle. It is called a Fermi problem, a method of estimating the scale of the unknown by breaking it into distinct, measurable variables. To solve this one, we need three things: the container, the unit, and the constraints. We cannot just guess here. Arriving at a number requires calculating the capacity of a unique 19th century building and reconstructing a mid-60s excavation standard. Structured logic allows us to take a lyrical joke and turn it into a calculation of cubic meters and historical digging standards. Our first variable is the container. The Victorian design of the Royal Albert Hall creates an immediate geometric challenge. It is not a simple, easily measured box. This diagram maps the physical dimensions of the building. The foundation is a massive ellipse measuring exactly 83 meters long by 72 meters wide, capped off by a 41-meter-high glass and iron dome. If we calculate the volume using pure geometry, treating the building as a perfect solid half-ellipsoid, we arrive at an inflated estimate of over 128,000 cubic meters. But theoretical geometry ignores the reality of the floor plan. Inside the actual hall, you can see how much of that space is consumed by steep tiers of seating, private boxes, structural supports, and the massive acoustic discs hanging from the ceiling. When we account for those internal structures, we can lock in our first variable. The documented volume of the main auditorium is exactly 86,650 cubic meters. The first step of our calculation shows why estimation requires adjusting for physical interference rather than relying on perfect shapes. Now we need the unit. We have to determine what a generic hole actually looked like when the lyric was written in the mid-1960s. In 1965, manual excavation had standard classifications. The most common category used for utility work, fence posts, or planting trees was the medium shovel-dug hole. This diagram illustrates the dimensions of a standard medium hole, 18 inches in diameter and 3 feet deep. By treating this dirt pit as a perfect cylinder, we calculate its volume, giving us a baseline unit of 0.15 cubic meters. Converting the physical act of digging into a fixed mathematical unit is what allows us to run the numbers for the entire building. This animation shows the core calculation. If we take the hall's 86,650 cubic meter volume and divide it by our single 0.15 cubic meter cylinder, we get a theoretical answer of 577,667 holes. But there is a physical constraint. If you attempted to dig actual holes into the two-dimensional ground floor of the venue, you would reach the limit of the foundation after digging roughly 28,500 of them. To fill the entire space, we have to treat the holes as physical objects and pack them into the three-dimensional airspace of the room. This cross-section shows the reality of stacking cylinders. They do not fit perfectly flush. Because of their curved edges, they leave diamond-shaped gaps of empty space between them, resulting in a volume penalty of 20 to 30%. When we apply that penalty to account for the lost space, our adjusted estimate rises to between 577,000 and 750,000 holes required to occupy the entire volume. The Fermi approach demonstrates how surreal questions can be answered through structured logic. By identifying the right variables, even a pop culture myth follows the laws of mathematical estimation.